Hello and welcome. My name is John Horvath, and the title of my presentation today is Small Angles, Large Benefits. It's about the unique behavior of tapered piles. Tapered piles, and I'm talking here about driven piles, and the driven part is very important. We're talking about piles installed by conventional impact driving. They are sometimes called conical piles in some of the older literature, but tapered piles are the oldest type of deep foundation. They've been in use for over 7,000 years. The technical and cost benefits of using tapered piles, what we refer to colloquially as taper benefit, is primarily in what we call friction or floating pile situations involving predominantly coarse-grained soils. The efficacy of tapered piles in fine-grained soils, or predominantly fine-grained soils, is still subject to question. Some people say yes, some people say no. So that's an unresolved issue, as I'll note toward the end of my presentation. In any event, taper benefit was recognized, at least in the United States, late in the 19th century. And this was a time frame where here in the United States, pile driving contractors were experimenting with then new materials such as Portland cement concrete and steel as alternatives to the timber piles that humans had used for some 7,000 years. So there was a lot of product development and patents from the late 1890s into the early years of the 20th century. It's interesting to note, of course, the time frame we're talking about. There was no soil mechanics as we know it today. There was no geotechnical engineers as we know them today. In fact, foundation engineering was treated as a subset or an area handled by structural engineers. And deep foundation work was typically contracted out to pile driving contractors who guaranteed the performance of the foundation. It's kind of interesting to see that we have come full circle to this nowadays, where you have specialty foundation contractors guaranteeing the performance of different types of foundations, especially when they're drilled. It's interesting that analytical methods for dealing with tapered piles did not come into existence until the middle of the 20th century. And this coincided with the birth of what I call modern foundation engineering, analytical foundation engineering in the 1950s. Unfortunately, although analytical methods for tapered piles have existed now for over 60 years, they leave a lot to be desired. They do not adequately and fully include all the very unique behavioral aspects of tapered piles, especially as regards installation methodology and the residual loads that develop from installation. And I'm going to be talking quite a bit about residual loads throughout this presentation. They are the proverbial elephant in the room that we've known existed since the 1950s, yet we don't like to talk about when it comes to deep foundations. But the problem with the existing methodologies up to the present for tapered piles is that they rely on the typical wished-in-place type of approach to resistance forecasting. And as we'll see, this leaves quite a bit to be desired. Well, because of the fact that analytical methodologies really have not caught up with everything that tapered piles can do, I feel that tapered piles are quite underappreciated and underutilized around the world, including here in the United States, where a lot of this early development over 100 years ago took place. And I think the reason for this is that a lot of the key elements as regards to installation methodology and the benefit of residual loads are really not fully appreciated. So tapered piles simply are not thought of or used to the extent that they could or should. So the overall objective of this presentation is to illustrate the current state of knowledge of what I consider the very unique behavioral aspects of tapered piles. And hopefully what will come out of this is that there will be a greater global awareness of taper benefit that leads to greater use of tapered piles, as well as future development of resistance forecasting methods that are superior to what we have to work with at present. I've organized the presentation into several segments, and this is to present the material in a logical, coherent framework. Also, to help those of you who are viewing this presentation, you may find it advantageous to watch it in segments as you have time and interest to do so. Well, let's start off with some basic definitions. First and foremost, when I use the term pile, I mean a driven pile, and driven pile meaning a pile that is installed by traditional impact driving for its entire length. This is common colloquial usage here in the United States, where just the word pile implies a driven pile. But I emphasize this terminology because I do appreciate that most of the rest of the world outside of the United States, the word pile is used for all types of deep foundation elements. So it's necessary to say driven pile or bored pile, what we call a drilled shaft here in the United States, or a jack pile, augered pile, torqued in place pile, whatever. So you need to get that terminology straight up front. I summarize here some of the key terminology that I use throughout this presentation. As we know, there's quite a variation in terminology that's used for deep foundation elements throughout the world. I use the words head and toe to indicate the two ends of a pile shaft. I think they translate well into any language, so they're good terms to use for these geometric elements. Resistance, as I use it in this presentation, is essentially what the ground provides to support the pile. And there's toe resistance and there's shaft resistance. The shaft resistance is what a lot of people call positive skin friction. So shaft resistance and positive skin friction mean the same thing. Drag loads are the same as what a lot of people call negative skin friction. And as you know, drag loads come from two sources. Most people know about down drag, and down drag is when the soil around the shaft settles more than the pile shaft. And that usually occurs when we have a fine-grained soil and we place some stress on the surface, some load on the surface, and this causes primary consolidation of the soil, and the soil literally drags along the shaft. Much less known, but actually much more common, is the drag load that develops as the result of residual loads from installation. And as I said earlier, residual loads, which I will talk about quite a bit in this presentation, are the elephant in the room in foundation engineering. We've known about them from the 1950s. As I'll show you, they exist pretty much with every type of deep foundation, not just driven piles. And yet we conveniently ignore them, both in routine practice as well as academic research. In this presentation, I reserve the term capacity for basically the loads that are applied here at the head of the pile. Since we are talking about tapered piles, we need to define taper, because there's at least 10 different ways that I found to define taper. I like the angular definition taper, as I've indicated here, where the angle is expressed in degrees of angle. I find this is very versatile because there's a lot of tapered piles where the taper is non-uniform. So we need to have a way to express variable taper along the shaft, and angle works very well for that. And one of the things you notice is that these are very small numbers. And This is why I say when it comes to pile taper, a little goes a long way, and that's why I titled this presentation, Small Angles, Large Benefits, because the types of angles that we're talking about for taper angle alpha are really quite small, and yet they have an outsized benefit in the performance of the pile. Well, let's next talk about pile types. I'm just going to summarize key elements because there are any number of books that do a much better job of showing you a lot of photos of piles, things like that. So I will just direct you to other references where you can look at pictures of the different types of tapered piles. First of all, in terms of pile categories, there are three different categories for tapered piles. They can be continuously tapered from head to toe, and that taper can either be uniform or variable along the pile shaft. Typically, a uniform taper angle is a manufactured pile made out of concrete, Portland cement, concrete, or steel, whereas typically a variable tapered pile is a natural pile, and this would be a timber pile. Partially tapered piles, some people call them semi-tapered, have both a tapered section and a constant perimeter section. And generally the tapered section is the bottom part. It is below the constant perimeter section. And I point this out because several researchers in recent years have suggested that the reverse arrangement would provide greater taper benefit. That is, the upper portion should be tapered and the lower portion should be a constant perimeter. I find this to be very highly questionable. If you look at the references where this recommendation or suggestion is made, you find that they're based solely on either very small scale laboratory tests. I'm talking about model piles in a 1G environment in a laboratory sandbox, and maybe the pile is 12 inches, 300 millimeters long. Or it may be solely some theoretical exercise or some theoretical solution that has some issues with it that I'll address towards the end of my presentation. The point being is that there is no full-scale piles that I'm aware of that have been installed with a tapered upper section, constant perimeter lower section to support this suggestion. So I would proceed with caution with accepting this as fact. And finally, we have what I prefer to call pseudo-tapered piles, where the shaft consists of multiple constant diameter increments or steps that approximate overall a continuously tapered pile. Now, in the published literature, you'll often see a pseudo-tapered pile referred to as a step-tapered pile, but I'm staying away from the term step-tapered because step-taper was actually a part of a U.S. registered trademark for a very specific brand of pile that was very dominant here in the United States for much of the 20th century. So as a result, if you say step-tapered pile in the United States, people will tend to think about a Raymond step-tapered pile, which was a very common pile type throughout much of the 20th century in the United States as well as elsewhere. And although these piles are no longer marketed commercially, they still exist in countless structures throughout the United States and elsewhere. So we do have to be a bit careful about terminology, because if you said step-taper to an American Foundation engineer, she or he would think you were talking about a Raymond step-tapered pile, not a generic step-tapered pile. Now, throughout this presentation, when I refer to tapered piles, I am talking about all these types of piles collectively. If it's important to talk about a specific geometry, I'll be very careful to do so. But when I talk about tapered piles as a group, I'm including all continuously tapered, partially tapered, and pseudo-tapered piles in that term. As far as pile materials, the materials that have been used commercially for tapered piles are wood, steel, and Portland cement concrete. In recent years, people have experimented in academia with more exotic materials, different types of polymers or plastics, as well as different, carbon fibers and this sort of thing. These have not been used commercially to date. They have not been viable to date, simply because of installation issues. When you use some of these alternative materials, you cannot drive on them using conventional impact driving. You have to resort to some unusual or exotic way of installing the pile. Timber piles, which years ago in the United States used to be referred to as wooden piles, they used to be untreated, but for certainly a very long time they are treated with a chemical preservative. Steel piles can either be a thin wall shell or a thick wall pipe. Now, I do want to point out that certainly here in the United States, foundation engineers, foundation contractors tend to use the term shell and pipe interchangeably, synonymously. They are really, for our purposes in this presentation, not synonyms. A thin wall shell, think of a very light piece of steel that you would use for, say, a drainage pipe. These require some type of temporary driving aid, what we call a mandrel for installation. The steel is so thin you can't drive on them directly. Whereas a thick wall pipe is inherently drivable without an aid because of the thickness of the material. Now, these steel piles can either be conventional hot rolled steel or cold form steel. They're always driven with a closed toe, and they're always filled with fluid concrete after installation. The use of cold form steel for tapered piles in the United States, going back to the 1920s, this is unusual for deep foundations. Typically, when you see some type of steel, whether it's a shell or pipe used as a deep foundation, steel pipe piles, for example, these are always hot rolled steel. So the use of cold form steel is kind of an unusual or anomalous situation with tapered piles. And finally, we have concrete piles, Portland cement concrete piles. These are always precast, but there can be a variety of casting techniques. You can use conventional casting beds. You can use, they can be spun cast. They can be reinforced in a variety of ways. Normal reinforcement, pre-stressing. The pre-stressing can be post-tension, pre-tension. So there's lots of variations with Portland cement concrete piles. In terms of pile geometries, pile materials can be configured in a variety of ways. You can have either a circular or a square cross-section, and I do want to point out that one of the things you don't hear talked about very much with tapered piles is that the cross-sectional geometry seems to play a role. Tapered piles with a square cross-sectional geometry have been used to a fair extent in some parts of the world. There is some evidence that they do not perform as well in terms of taper benefit as those with a circular cross-section. So you'll see at the end of my presentation that this is certainly one of the issues that needs to be resolved in the future. They can have a solid or hollow cylindrical cross-section, and by hollow cylindrical I'm talking about the final pile geometry. I'm not talking about steel pipe piles where you drive the hollow pipe and then you fill it with fluid concrete after driving. I'm talking about a pile that remains hollow throughout its life, and these are typically precast concrete piles that are spun cast. The piles can be more or less cross-sectionally homogeneous, and I would lump a reinforced concrete pile as being nominally homogeneous, or they can be composite, meaning they have multiple components. And this would typically be, again, your steel pipe pile or steel shell pile, where you drive the shell or pipe first, and then after it's driven, then you fill the core with Portland cement concrete. Finally, the piles can be longitudinally homogeneous, or they can be longitudinally hybrid, what I call hybrid piles. Now, I do want to point out that hybrid piles, or what I refer to in this presentation as hybrid piles, you will see in the older published literature referred to as composite piles. Please be careful. I use the term composite in this presentation in a very different manner. I use composite to mean a multi-component cross-section, not where you have two very different piles stacked one above the other. That's what I call a hybrid pile. Now, as I said at the outset, tapered pile designs have been evolving since the late 19th century. Of course, for 7,000 years, humans just had timber piles, which are naturally tapered. That's the way tree trunks grow. But tapered pile designs have been evolving since some of the early research in the 1890s here in the United States, and this continues to the present. This is not a static technology. In a book that I've recently published on tapered piles that I'll reference at the very end of the presentation, I summarize all this early U.S. patent work, as well as much more recent, within the last 20 years, recent developments such as the taper tube pile. I would recommend Chellis's book, the second 1961 edition, really gives you an excellent summary of the Raymond Standard, Raymond Step Taper, and monotube piles that together collectively really dominated the manufactured taper pile market in the United States for much of the 20th century. The Raymond Standard pile in particular grew out of some of this early U.S. patent work in the 1890s, and these three pile types really dominated tapered piles in addition to timber piles in the United States and elsewhere for much of the 20th century. And really, Chellis gives you an excellent treatment of this subject. Chellis also talks about what I call hybrid piles, what you'll see called composite piles in older literature. And these consist of a constant diameter extension or upper section, usually with some sort of Portland cement concrete filled steel pipe or shell that was placed on top of a timber pile and that was generally untreated. Hybrid piles were a generic low budget type of tapered pile, very extensively used in the United States, especially in the first half of the 20th century. The idea is that you would take an untreated timber pile, which was about as cheap as you could get. You would drive that into the ground below the permanent groundwater table. And this was based on the traditional assumption that wood, if it is buried in the soil below the permanent groundwater table, will not deteriorate. Unfortunately, we know that this is not true. There has been some interesting research, predominantly in Western Europe and more recently in the United States the last few years, that show that untreated wood, even if it's buried in soil below the permanent groundwater table, will deteriorate in the long term. And we're talking about 100-year or more time frame here. So the hybrid pile would drive an untreated timber pile below the groundwater, and then they would place a steel pipe or shell on top of it, fill it with concrete. Very labor intensive. It was overall economical in the past, certainly has not been for a very long time. The next topic I want to talk about is site characterization. Site characterization is always the first thing to think about on any foundation engineering project. It's the cornerstone of every successful foundation design, no matter what type of foundation, shallow or deep, no matter what size the project. There's no analytical method that can compensate for inadequate site characterization. The fanciest three-dimensional finite element analysis in the world is worthless if you don't have good input data for that to characterize the ground that you're talking about. Unfortunately, one of the downsides of recent years is that there's been a backsliding in the quality of site characterization performed routinely in practice. There were tremendous gains made in the last few decades of the 20th century, but in the early years of the 21st century, there seems to be backsliding. Appears to be a combination of taking site characterization for granted, treating it as a commodity to be done, do the least possible that you have to at the least possible cost, outsourcing it to low bidders, things like that. And this opinion of mine is not unique. Just within the last month or two, in one of the trade magazines, Geostrata, that's published by the ASCE Geo Institute, there was a very telling article by two experts in the field, and you'll notice that the subtitle here, Have We Regressed from Decades Past? And the authors make a point along the same lines that I've mentioned, that there has been, for a variety of reasons, regression in this area. So this is why I'm emphasizing the importance of site characterization, and specifically if we're going to improve what we do with tapered piles in terms of analytical methodologies and resistance forecasting, there really are two what I consider to be overarching goals that we have to accomplish. Number one, we have to move on from the standard penetration test and SPTN values. There's been this, what I feel is an obsessive over-reliance on SPTN values, especially in coarse-grained soil. In my opinion, the standard penetration test is good for one thing. You get soil samples to look at. You might do some water contents, perhaps even a particle size distribution curve, but that's it. There's really little value to be gotten from the standard penetration test other than the fact that you get to see the soil that you're dealing with. Again, my opinion in this matter is not unique. Professor Paul Main, who is probably one of the world's greatest authorities on site characterization, this was from a 2012 presentation. Paul has made the same point many times in many different presentations in recent years, that in geotechnical engineering, for some reason, we cling to old things. Now, here he used a comparison between 1948 and 2012. We could go back another 20 years or so from 1948, and we would still be using the standard penetration test. And we could advance 8 years to the present from 2012, and all of these things, cell phones, automobiles, TVs, they've all improved, and yet what are we still doing? We're still banging the standard split spoon into the ground, counting the blows and using those blows very oftenly as the basis for our designs. And again, not saying that we should just abandon something because it's old. We need to take a hard, critical look at, is really this the best we could do? And the answer should be no. We really need to do more to bring the laboratory to the soil in the form of in situ testing, rather than the traditional other way around, getting soil samples we bring to the lab. I'm not against laboratory testing by any means, but as we know, certainly for coarse-grained soils, laboratory testing has very, very limited use. And for fine-grained soils, unless you're willing to invest in some very, very high-quality laboratory testing. And this is the point that de Groot and de Jong made in their magazine article recently, that unless you're willing to do very high-quality laboratory testing on fine-grained soils, you need to take a hard look at things. And there are dozens of invasive and non-invasive in situ tests that we can use routinely. These are not just research tools anymore. In my opinion, at the very top of the list for tapered piles is various types of cone penetrometers. Anytime that you're dealing with a potential tapered pile project, the cone penetrometer should be at the top of the list of in situ testing devices to use. That's the first choice. And that's simply because in the types of soil conditions where you're likely to use tapered piles as a friction or floating pile, you can perform cone penetrometer soundings. And there are a number of reasons for this. First of all, you can get dozens of soil properties and parameters related to coarse grained soil that for all practical purposes are impossible to get from traditional soil sampling and laboratory testing. Nowadays, in most areas, we have some seismic considerations, seismic liquefaction especially, and the results from cone penetrometer soundings provide superior correlation with liquefaction assessments as opposed to the now almost 50-year-old correlations for the standard penetration test N values. And especially the cone penetrometer gives you insights into what we call microstructure, the aging and cementation of soils. And I'll touch more on this in a minute. Cone penetrometer really is an outstanding complement for fine-grained soils. Again, I'm not against laboratory testing, but we should do it laboratory testing on a cost-effective basis. And by combining laboratory testing with cone penetrometer soundings, we could get a lot more information at a lot lower overall cost. Again, I emphasize that cone penetrometer soundings are not just for quote-unquote big projects. They're cost-effective for very, very small, modest projects. Just a few years ago, I was involved in a local project here in the New York City metropolitan area, and there was just maybe half a dozen borings. There was two cone penetrometer soundings. That was it. And the amount of information gotten from that was really quite worth the cost. Last but not least, when you do cone penetrometer soundings, for gosh sakes, use the values. I've seen in recent years been at presentations where practitioners talk about, well, we went to the site, we did borings, SPTN values, we did cone penetrometer soundings, and here's how we designed the piles using SPTN values. No mention at all of using the cone penetrometer data. So they spent the money to do the cones and yet didn't use the results. A very quick primer on cone penetrometers, I know you all know what I'm talking about, but just so we have some common terminology. What I refer to simply as a CPT, the cone penetrometer, is just a basic two-parameter tip resistance and sleeve friction that has its roots going back to the 1930s in the Netherlands. The so-called piece of cone with the pore pressure sensor in what we call the U2 location just behind the tip, some people call it the collar location, has been the basic minimum standard of practice for some time now. The seismic piece of cone has really entered the mainstream of availability. It is no longer just a research device, and you should be doing some seismic piece of cone soundings on at least a portion of the total number of cone penetrometer soundings on every project. The small project that I mentioned a minute ago in the New York City area that I was involved in, we did one piece of cone sounding and one seismic piece of cone sounding. And the same rig, the rigs are set up to do both types of soundings. And again, this was a small project and there was tremendous value for the money. Despite the tremendous advances in the cone penetrometer hardware, the biggest advances really have been in decades of developing empirical correlations for dozens of soil properties and parameters, especially for coarse-grained soil. The focus has been primarily on coarse-grained soil due to the inability to measure a lot of useful parameters in traditional laboratory testing. More recently, there's been a lot of work done with fine-grained soils as well, developing correlations that complement and can be used with laboratory testing. Again, you get a piece of data about every 1 to 2 inches with a cone penetrometer soundings. And when you do shear wave velocity, capital V sub S is shear wave velocity. That's the basic measured parameter in a seismic piece of cone sounding. Typically, you get them every meter or about 3 feet. One of the benefits of doing a seismic piece of cone is not only do you get the same data you would with a piece of cone, but you get tremendous insight into soil stiffness and microstructure. And I'm emphasizing the soil stiffness because, as you'll see in the conclusion of my presentation, I think one of the areas where we're headed with deep foundations is to design based more on stiffness as opposed to the traditional soil strength. Of specific relevance for deep foundations is that you could use the measurements in a piece of cone or seismic piece of cone sounding for what we call direct methods for resistance forecasting, and I'll elaborate on this a bit later. And again, soil stiffness in the form of shear modulus G has really emerged as one of the most important soil properties for all types of deep foundations, even more so than soil strength, believe it or not. And what we get from the seismic piece of cone, as I'll show you, you measure the shear wave velocity, and from this can calculate what we call the small strain or quasi-elastic shear stiffness. Now, in most of the world, the small strain shear stiffness is called G sub O or G sub naught. Here in the United States, we tend to call it G max. These two parameters are one and the same. If you haven't done so already, I strongly suggest that you spend about an hour or so of time and listen to the webinar by Professor Ken Stokey that he put on for the ISS MGE about 3 years ago. You can go to the International Society's website and access that webinar at your convenience, and there is no cost. Well, just to give you a few examples, again, there are dozens of soil properties and parameters that you could get. I'm just going to go through a few for coarse-grained soils just to show you a little bit about the benefits of using cone penetrometer soundings. And I'm going to be using Kennedy Airport in New York City as an example for this. This is a typical profile at the airport, which was developed in the 1940s by hydraulic filling on a marine tidal marsh. You have medium defined sand fill that was placed hydraulically. You have a relatively thin stratum of organic clay with some peat, and this is underlain by 100 plus feet, 30 plus meters of a Pleistocene stratum referred to as the upper glacial aquifer. More recently has been broken down into 3 formations, the Belmore, the Wantoa, and the Merrick. And you can see typical profiles of field end values. In this case, they correlate to N45 values. And this is an uncorrected tip resistance that has been non-dimensionalized to atmospheric pressure. So it gives you, this is a very, very typical profile throughout most of Kennedy Airport. If you'd like to learn more about Kennedy Airport, and this has really been an excellent case history for tapered piles, because in the almost 80-year history of the airport, they've used timber piles, monotube piles, tapered tube piles as the deep foundations of choice. And these piles are typically embedded within about the first 40 feet or so of the upper glacial aquifer. If you'd like to learn more about Kennedy Airport and all the geotechnical and foundation engineering lessons learned, especially with regard to tapered piles, really elaborates on a lot of the things I'm talking about in this presentation. I do have a narrated PowerPoint presentation that is available on my YouTube channel, where, of course, you found this presentation. Just look for the presentation titled From Wetlands to Wings and a River Ran Through It. It's about Kennedy Airport. When we deal with coarse-grained soils, and again, Kennedy Airport is a very classic situation where we use tapered piles, a friction or floating pile scenario. And if you're curious, bedrock is something like 1,000 feet below the ground surface, so something like 300 meters below the ground surface. So very, very classic friction or floating pile scenario in coarse grained soil. Typically, when we talk about sands, one of the first things we're interested in is relative density. Possible to measure in the laboratory on a routine basis, but with cone penetrometer soundings, you could use the data with empirical correlations, and here you see a profile of the estimated relative density as a function of depth. However, when it comes to the consistency of coarse-grained soils, especially sands, more recently we prefer to use what is called the state parameter psi, and this is a parameter from critical state mechanics. And essentially, state parameter says, where are you in the behavior of a sand? Are you contractive, meaning that when you apply a shear stress, you're going to get a volume decrease? Or are you dilative, where if you apply a shear stress, you're going to get a volume increase? Theoretically, that dividing line is 0. Traditionally, people use a value of minus 0.5 as a somewhat more conservative dividing line. Obviously, you don't jump from contractive to dilative. In infinitesimal distance, there is some transition. So here we see one of the things, again, we could get from cone penetrometer data, we can get an estimate of the state parameters, a function of depth, and that's what you see plotted here. And the reason the state parameter is more insightful is there's a very definitive line for saying where we have contractive or dilative behavior. And of course, contractive behavior is of concern with regard to, say, seismic liquefaction. So, for example, we have a contractive zone here. And certainly at Kennedy Airport, this is a zone where we would be concerned about seismic liquefaction, which is why piles there nowadays have to go to greater depths. But it is interesting to note that this contractive zone does correlate very nicely with some of the lower relative densities. And again, another contractive zone down here correlates very nicely with lower relative densities. So certainly, when you're looking at the consistency of coarse-grained soils, especially sands, nowadays you do want to focus more on state parameter, not relative density, as we have in the past. Stress state, always important. Here's a plot. The brown line is the calculated overburden stresses. And by the way, one of the nice outputs you get from cone penetrometer data is it could give you an estimate of soil unit weights. You don't have to guess what the soil unit weight is. And in fact, this overburden stress line was calculated using calculated or estimated soil unit weights, which will vary with depth, of course. Here you see the red dots are the yield stress, what we used to call the maximum past effective stress or pressure, natural pre-stress. There's all sorts of terms and notation used for this. Again, yield stress is something that historically is impossible to measure in a coarse-grained soil, and here we can infer it from the cone data. And of course, that allows us to calculate the yield stress ratio, what we used to call the over-consolidation ratio. And here you see a plot of yield stress ratio versus depth. Another useful parameter when we're talking about soils is the over-consolidation difference, OCD, over-consolidation difference. And that's simply the numerical difference between yield stress and overburden stress. What this does is to give you an idea of, is there a pattern to the overstress or pre-stress in a given area? That's the primary benefit of OCD. However, I would say that the most significant stress state parameter is K sub O, the coefficient of lateral earth pressure at rest. Difficult, if not impossible, to measure for pretty much any type of soil. but we can infer it from cone penetrometer soundings. And as we'll see as this presentation evolves, this is turning out to be a very, very crucial parameter, actually much more important than yield stress or OCR or yield stress ratio for coarse grain soils when we're dealing with tapered piles. Really, Quesabo is emerging as an essential soil property for state-of-the-art methods for forecasting the geotechnical resistance of all types of deep foundations to axial loads, not just tapered piles. Drilled shafts, augered piles, any type of deep foundation in both compression and uplift. And the reason I say this is because we now understand that Quesabo governs both the shaft resistance, because it influences K sub H is the coefficient of lateral earth pressure acting along the shaft of the deep foundation after installation. Nowadays, we prefer to use the KH over K0 ratio. Essentially, the KH-KO ratio says how much did K sub H increase due to the installation of the deep foundation element, but relative to the original KO. And Kolhowie, the late Professor Kolhowie, decades ago showed that much more insightful for all types of deep foundations was not K sub H per se, but what is K sub H relative to the KO that you started from. And if you think about it, that makes sense. When you install any type of deep foundation in the ground, controlling what the final lateral earth pressure coefficient is going to be is to some extent what the lateral earth pressure was before you started, what the virgin site condition, KO conditions were. And that's what the KH-KO ratio reflects. So this is really nowadays, and you can see how it relates here to sigma H bar effective horizontal earth pressure. The KH-KO ratio is evolved in recent decades to really be of critical importance to all types of deep foundations. But in addition to shaft resistance, I will show you later in this presentation that, believe it or not, lateral stresses, as reflected in KO, also control the toe resistance of all types of deep foundations. So this is why I'm emphasizing the importance of KO, and of course the great benefit that you can estimate KO based on cone penetrometer sounding. Let's talk now about ground stiffness or modulus. As I said, this has been emerging as really a very critical soil property for all types of deep foundations, not just tapered piles. So when you perform a seismic piezocone sounding, you get the shear wave velocities V sub S, and these are the red squares that you see plotted here. Again, this happens to be for a site at Kennedy Airport, New York City. And then using the theoretical relationship where shear modulus is equal to the density of the soil. And again, density, you don't have to guess at. You don't have to assume. You could get estimates of soil density from seismic piezocone soundings in both coarse and fine grained soils. And this is shear modulus squared. So from this, we get a plot of G sub O, or G max if you prefer, the small strain shear modulus as a function of depth. And that's what you see both with the yellow triangles and red squares. I just use two different, I use mean data and median values of data to calculate, and essentially gave the same results. And as I said, the reason I'm emphasizing small strain shear modulus is that this has emerged as being an essential property for state-of-the-art analytical methods for all types of deep foundations in compression and uplift, and not just tapered piles. And really, the seismic piezocone is a very cost-effective tool of choice for this, because not only do you mention shear modulus, but you get all the benefits of a seismic piezocone sounding at the same time. Some additional comments about ground stiffness. Some of the newer, more exotic parameters that we look at. This is just an empirical parameter, I sub g, that gives us an idea of microstructure. Again, microstructure is the term that we use to collectively refer to aging. As we know, the older the behavioral age of a soil, the stiffer will tend to be. And separately, you may get some cementation as a function of time as well. This is another factor. ASF is called the age scaling factor. Again, these are all for Kennedy Airport, very typical results. And the reason for this is that we've increasingly found that it's important to differentiate between the behavioral versus geological age of a soil stratum. Now, all soil strata have one geological age. It's simply when nature created that soil stratum, or if the soil was placed as the result of human activity, when did humans place it, which tends to be in the Holocene or recent. However, the behavioral age can be different. And the reason is that behavioral age of a soil stratum can be reset. And it can be reset by any number of natural phenomena such as seismic liquefaction, stress increase, stress decrease, as well as human activity. And the reason for emphasizing behavioral age, and this is what we're plotting here, we're plotting the behavioral age. And what's interesting to see is that, for example, in this upper glacial aquifer, which goes from about 5 meters down to 30 meters in this plot, so from about 16 feet down to about 100 feet or so, these were all Pleistocene soils. However, as we see, as we get closer to the bottom of the stratum, the behavioral age, which is what is being reflected here, appears to be older. And the reason for emphasizing behavioral age is we now understand that this affects seismic liquefaction and deep foundation performance. Essentially what we're saying is, all things being equal, if you have two soil strata of the same geological age but different behavioral age, they will behave differently in an earthquake, and they will behave differently in terms of how they support a deep foundation. And again, this is a real paradigm shift because we're talking about soil stiffness here. You know, when we talk about deep foundations, we tend to obsess on what's the strength, what's the phi angle, what's the undrained shear strength, right? Deep foundation design, going back to the 1950s to the present, is based on strength. So it's a real paradigm shift, and I'll talk more about this toward the end of my presentation, to think about soil stiffness. But it turns out soil stiffness plays a significant role with deep foundation performance. And again, this is why I'm perhaps belaboring the point or emphasizing the point, is that not just for tapered piles, but for deep foundations in general, we really need to pay a lot more attention to the stiffness of the ground. And really, we can only get this sort of insight from a seismic piezocone sounding. And I tell you, you can't get it from SBTN values. And you can't just get it from Q sub C, the uncorrected tip resistance of a cone penetrometer sounding. These aging or microstructure effects do not show up in SBTN values. They do not show up just in the tip resistance of a cone. They only show up when you do shear wave velocity profiles. I'm now going to talk about axial resistance. This will be by far the longest segment in this presentation because this is the topic that has seen the most revolutionary, greatest change with regard to tapered piles in particular. So we need to spend quite a bit of time on this. Let's say at the outset that the perception that has guided foundation design around the world up to this time, deep foundation design, that there is a unique single-valued geotechnical failure load, or ultimate limit state, as I prefer to call it, and axial compression is simply a myth. And I repeat, it's a myth. The reality is that the geotechnical ultimate limit state is at best a range in values, and in some cases the point has been made that it does not appear to exist at all. And I think we need to stop for a moment and think about this at length, because if anything, in recent years there has been a migration toward LRFD design in foundation engineering in general and deep foundations in particular. And this is true around the world. And LRFD, by its nature, demands that every system component, every material has a well-defined, single-valued failure load, failure stress, however it is presented. So LRFD is a design methodology that is based around the concept of single-valued, well-defined failure loads. And while this may work for many structural materials or structural systems, it has always been problematic for geotechnical engineering. Now, that has not prevented people and code bodies from imposing LRFD on geotechnical and foundation engineering. But it does indicate that when you apply LRFD to foundation engineering in particular, that you have a real problem, because what it means is that when you talk about the axial compression of a deep foundation element, you must pick out a single valued failure load, ultimate limit state, where in reality there is at best a range in these values. So there's a tremendous amount of subjectivity, and I'm going to illustrate this position of myth with several examples. Well, let's look at this from several perspectives. First of all, the traditional static load test is assumed to be the gold standard, if you will, for defining the geotechnical ultimate limit state. When all else fails, you perform a load test. You measure, quote unquote, the failure load of the deep foundation element. However, the static load test is about as non-standard as the standard penetration test. You know, one of the great revelations of the later 20th century was that the standard penetration test is anything but standard. We now realize that there are any number of variables in that test, so you could get a whole range in N values for the same soil conditions. It's pretty much the same thing I'm pointing out here. For the same deep foundation element and the same soil conditions, you can get a pretty large range in outcomes. There's variations in the setup, what I call the mechanical elements of a load test, the hardware and the setup, and as well as the load application protocols. The net result is you get a wide variety of outcomes, and this graphic is just a qualitative illustration of this. To begin with, you could get 20% or more variation in the measured load depending on how you measure the load. Now, we've known since at least 1970, if not earlier, that we should be using electronic load cells, not relying on jack pressure. Believe me, I see in U.S. practice to the present, people still rely on jack pressure measurements. And it's been well documented that you could get 20%, 25% error. The jack pressure is always wrong. It's always too high on the unconservative and potentially unsafe side. You get 10% error in measuring the settlement of the head of a deep foundation element when you use dial gauges or a tension wire and mirror, whatever. Again, this is well documented, and that's simply because the The so-called reference beams that you use for the dial gauges or tension wire, whatever, that reference beam will settle somewhat during the load test. It's inevitable. So the point I'm getting at here is that just in the mensuration systems of load and settlement, you're going to get some significant errors. So you may think this is the failure load. Again, if you use some failure criterion based on settlement, as we do both in the United States, where we use the so-called Davison offset limit, or in Europe, where they tend to use a toe settlement criterion. So when you use a settlement-based criterion, you might infer one so-called failure load, where in reality this is the failure load. So you see you have a range here, just based on how you make the measurements of load and settlement in the load test. Even if you say, okay, I have a single load test curve that I'm happy with, how you interpret that curve gives you a range in ultimate limit state or failure values. This is an example. This happens to be a drilled shaft or board pile. And this just shows you there's at least a dozen, if not more, different criterion for defining the ULS or failure load in a load test from a load test curve. We see here in this example there's a range of over 200% in calculated outcomes, with the popular settlement-based criteria used in the US and Europe falling somewhere in the middle here. Again, this is not new information. We've known this for decades, that you can get a huge range in interpreted outcomes. And I think you would agree that this range, which is over 200% in this case, is not uncommon. This is far greater than any load or resistance factors. You know, I see people argue about, well, maybe this factor should be 0.35, but if I do a load test, I can make it 0.45. You know, we're arguing about very small numbers when in reality, the curve that we're talking about has a huge range in outcomes. Perhaps the most important thing I want to concentrate on here is that the physical mechanisms that we use to define the geotechnical failure of deep foundations really dates back to the 1950s. This was the beginning of what I call modern foundation engineering that was based on geotechnical engineering and calculations. Unfortunately, these mechanisms have been recognized for some time now to be incorrect and incomplete, certainly when it comes to tapered piles, and they really need to be revisited, revised, and updated. Well, let's go through this in some detail because I feel this is a really crucial aspect of this presentation. Let's first look at axial compressive loading of a constant perimeter shaft, right? Circle, square, whatever. This happens to be a model pile, and what you're looking at here is this particular researcher, Robinsky, was very common at one time, embedded lead shot in the layers of sand, and then took an X-ray basically. And the light-colored circles, this is basically the position of the lead shot prior to load application. The dark colored circles are the locations of the lead shot afterward. And I've just highlighted the pile here for clarity. So the traditional assumption is you apply a compressive load at the head of the deep foundation. It settles relative to the ground, and the key assumption is that the ground remains fixed. It remains spatially fixed. So the ground remains fixed, the pile or whatever type of deep foundation you have settles, and you develop the classical one-dimensional planar sliding friction at the interface between the outside of the shaft and the adjacent ground. And then we apply Coulomb drive friction using phi, c, whatever combination we want to come up with a unit shaft resistance, or what we call positive skin friction, if you will. Problem is that's plain wrong. We've known it's been wrong for Well, at least 1963, for example. The reality is that the load transfer between the shaft of any type of deep foundation and the adjacent ground really occurs as vertical shearing within a zone of soil. It is not occurring along some planar one-dimensional interface that you continue to see in textbooks to the present time. We have a zone of soil where this interaction is occurring. And in fact, the adjacent soil right along the shaft is settling as well. And although it's a bit hard to see, you could see the curvature in the dark colored lead shot. And I've just highlighted it with the solid yellow curve here. So the reality is that when the pile settles, the ground adjacent to the pile, or the deep foundation in general, will settle as well. Now, the deep foundation at some point will settle more than the ground, but the reality is that the ground is settling as well. And that's because this load transfer through vertical shearing is occurring within a zone of soil, not along some one-dimensional planar interface as we assume. And again, this is not new information. Rubinski showed it almost 60 years ago. In more recent research, these researchers used colored sand instead of lead shot, but you see the same behavior. You see the fact that as this model deep foundation element settles under axial compression, the ground in some zone adjacent to it settles as well. You get this very characteristic sort of settlement curve, settlement cone of soil. So the shearing is occurring within a zone, not some planar interface. Well, let's talk about tapered shafts, and this is really where we need to improve our understanding of what's going on. Now, it was recognized, at least by the early 1960s, that a tapered pile, and we can extend this to some extent to other type of tapered elements that are installed by perhaps jacking or torquing or even drilling. But we have to be careful, as we'll see. So I'm focusing now on the driven piles, as I said at the very beginning of this presentation. So almost 60 years ago, it was recognized that tapered piles develop shaft resistance from a unique physical mechanism. And that mechanism is different from the traditional shaft resistance mechanism of what I call sliding friction. I now refer to this unique physical mechanism as wedging. I think wedging is a good term to use for the mechanism by which tapered piles develop axial compressive resistance. And we could visualize that if we just imagine some arbitrary fixed plane in space. So we want to focus our attention just on a plane defined by the line x prime here. The physical mechanism of wedging is simply you have some object that has a shape broadly as shown, and you impact it with a vertical force. And the most classic common example, you have a steel wedge that you drive into a piece of wood, for example, a segment sewn from the trunk of a tree. You drive that wedge into the sawed log segment using a sledgehammer. So you impart a vertical force, and simply by virtue of the geometry of the wedge, you get a horizontal component to that vertical force, number one. Number two, the more you drive that wedge into this material, that horizontal force is going to increase. And for anyone who's either driven a wedge into a piece of wood or seen it done, the idea is you keep on driving the wedge until you increase this horizontal stress until it exceeds the tensile resistance of the wood parallel to the grain. And that's why the wood splits. It's a tensile failure. And you get that tensile failure because this wedge, simply through geometry, is increasing the horizontal stress. So this is what I call the wedging mechanism. It's a very simple, basic problem in physics, and it's well established. You drive the wedge in the ground, and relative to some fixed plane in space, you create and increase the horizontal stress. Well, we now understand that using this wedging mechanism, the taper benefit that I defined in a qualitative sense at the beginning of this presentation develops in two distinct stages for a driven pile. And this is why I emphasize the driven part. You get what I call stage 1 wedging during driving. Then you get a second stage, stage 2 wedging occurs during the subsequent axial compressive load application at the head of the pile after the pile has been installed in the ground. So stage 2 wedging is what occurs, say, during a load test or during a service load application on the pile. So now if we want to extend the generic wedging mechanism to tapered piles, now this fixed plane is somewhere in the ground, and we could see that we really develop wedging in two distinct episodes or stages. Imagine now we're driving the pile, and I think you could see that as you drive this tapered pile into the ground, or if you have a semi-tapered pile, this would be only, of course, the lower tapered portion. As you drive this tapered pile into the ground, you are increasing the horizontal or radial, in the case of a circular pile, stresses acting along the shaft as you drive it in the ground. This is why I emphasized at the beginning I was talking only about driven piles, because it turns out that most of the wedging and the benefits of wedging and most of the taper benefit occurs during driving. And the reason this is so important, it means that if you have installed this pile in some other manner, for example, a lot of the papers you see in the literature about tapered piles the last couple of decades involve little model piles, maybe 12 inches, 300 millimeters long, that the researchers buried in sand, in a little sandbox in a laboratory. So they didn't drive it, they just buried it in the sand. Well, what does that mean? Well, what it means is they didn't model this stage 1 wedging at all. And it's the same thing, there are some technical papers I'm going to reference later where the researchers referred to a drilled tapered element. Well, I think you could see if you basically create a drilled shaft or a bored pile that has a tapered geometry to the hole, you're not going to get the stage 1 wedging either. Well, the point I'm trying to make here is that most of the literature you see for the last 30, 40 years concerning tapered piles has either been based on model test or theoretical work or some case history comparison where the deep foundation was not driven into the ground. So the researchers completely missed the stage 1 wedging, which is really the predominant wedging that occurs with a tapered pile. And again, this is why I emphasized at the very outset of my presentation, I am only talking about tapered driven piles. Right? Because the taper benefit is not just, oh, I have a tapered whatever. The taper benefit really depends tremendously on how you created that deep foundation in the ground. And it is the tapered driven piles that have the unique, significant tapered benefit. If you have a tapered drill shaft, quite honestly, you're going to get very little tapered benefit. And this is what you see in the published literature. A lot of the published literature, you see only a very, very modest taper benefit. Well, that's because they didn't drive the model pile or whatever into the ground. So they missed most of the taper benefit. So I think the point's been made. And again, you will also get some additional, what I call stage 2 wedging and taper benefit under the post-installation loading. But really the bulk of the taper benefit occurs during driving. So the bottom line benefit of this wedging mechanism is that you increase the horizontal or radial pressure acting along the shaft of the tapered element. And this will increase until you reach what is called a limiting pressure, such as in a pressure meter test. So there is an upper bound to this, but as it turns out, you will never reach this limiting pressure with a tapered pile. You would have to either have such an extraordinary taper or have the pile settle to an extraordinary amount to reach the limiting pressure as you do in a pressure meter test. And again, I want to emphasize, because it is very critical, you cannot lump all tapered deep foundations together. That's really the point I'm trying to make here. The installation methodology is critical. And I've seen in recent years people have done things like they'll drive a tapered pile halfway using vibratory hammer and then switch to an impact hammer. You're not going to get the same taper benefit, because if you vibrate the pile halfway in the ground and then start to drive it, you're missing a good part of the taper benefit by the vibratory installation. So one of the things we've learned is that taper benefit is tremendously dependent on installation methodology. And you need to pay a lot more attention to it than literature of the last several decades would indicate. Well, we can extend this wedging concept to what I call unwedging, as the physical mechanism that occurs when a tapered pile is subjected to uplift after installation. And uplift loading of tapered piles is really one of the most badly handled, misunderstood things I've seen in practice. There's a certain element in practice that somehow imagines that if you apply an uplift load to a tapered pile, that it will somehow magically spring out of this tapered hole in the ground with little or no resistance. I have seen more than a few people say, well, I was going to use tapered piles, but they have no uplift resistance. Simply because of this imagined mechanism that once you create a taper hole in the ground, that hole will magically stay there as if it were frozen in space. And you could just lift the tapered pile out without any resistance. And of course, that's grossly incorrect. But at least by defining this unwedging mechanism, for the first time, we could rationally model and go on to look at the uplift resistance of tapered piles in a rational manner. And that has been seriously lacking in practice to date. And this little animation just shows you what the unwedging mechanism looks like. There's two takeaways from this. Number one, that yes, as you apply uplift to a tapered pile and you get this unwedging, that you will have a reduction in horizontal or radial stresses, but they do not suddenly decrease to zero. You think about it. If you have a retaining wall that has the at-rest lateral earth pressure on it, if you pull that wall away from the soil, what's going to happen? Well, the lateral earth pressures aren't going to drop to zero, are they? No, they're going to decrease to the active state and then remain at that active state no matter how much displacement. The other thing I want to point out here is, yes, although the horizontal stresses decrease, they are decreasing from an elevated level due to the stage 1 wedging. So the point to keep in mind is that because of the stage 1 wedging, which creates a very large initial horizontal or radial stress in the ground along the shaft of the pile, you're starting from an elevated level of confinement already. And if you don't want to believe me, believe some load tests that were done by Norwegian Geotechnical Institute in Norway more than 50 years ago. They had essentially identical tapered piles, precast concrete piles. One was tapered, actually semi-tapered. Well, they did both continuously tapered and semi-tapered, and they had constant diameter piles. Installed them in a relatively loose sand, And one of the remarkable outcomes, and I discussed this in my recent book on tapered piles, uh, is that, or you could go back to the original paper was an international conference in 1973, is that basically, in very simple terms, the tapered piles had essentially the same uplift resistance of a constant diameter pile. So this myth that somehow tapered piles don't have meaningful uplift resistance is just that, it's a myth. Well, of course, we would like to model this wedging analytically, and right now the best model we have for that is based on cylindrical cavity mechanics. Cylindrical cavity mechanics, and I'm illustrating it here using the basic case of what we call cylindrical cavity expansion. This is where we start from an initial cylindrical cavity and then expand it. So this is actually a very good model for what happens when you run a pressure meter test. That sometimes called the loading problem in cavity mechanics, that as you expand the cylindrical cavity, you increase the radial stress on the outside wall of the cavity. So this is the basic mechanism that we use for wedging. Although I don't show it, you could run this in reverse and you would basically see cylindrical cavity contraction or unloading. And that, of course, would be useful for modeling unwedging and uplift resistance. So we put these concepts together. We use the concept of wedging as the physical mechanism that defines what happens when you actually axially load a tapered pile. You have wedging or unwedging depending on the direction of load. We couple the wedging, unwedging with cylindrical cavity mechanics, and we conclude that stage 1 wedging that happens during tapered pile driving involves what we call cylindrical cavity creation, followed by further cylindrical cavity expansion. And then when we have post-installation axial compressive loading, we have additional cavity expansion. If we have unwedging due to post-installation uplift loading, we can model that with cavity contraction, or what is sometimes called unloading. And again, to tie these concepts together, I'm just superimposing the wedging mechanism on a still image of cylindrical cavity compaction. And what I'm trying to show you here is that reference to some arbitrary depth in the ground defined by the line XX prime in this graphic. You see that cylindrical cavity expansion or contraction really is a very good model for the wedging and unwedging mechanism that occurs with tapered piles. Well, I long ago concluded that shaft resistance due to wedging that occurs with a tapered pile and is modeled using cylindrical cavity mechanics really needs to be formally recognized in foundation engineering as what I call the third resistance mechanism for deep foundations. You know, since the 1950s, since modern computational foundation engineering has evolved, we've had two traditional resistance mechanisms. Shaft resistance due to sliding friction, which I've shown you now is not just one-dimensional sliding, but really a zone of sliding. And toe resistance due to end bearing that I'll talk about in a minute. We need to add shaft resistance due to wedging as a distinct third resistance mechanism. Now, there's a lot of people that say, well, no, it's really not a third mechanism, it's just a modification of sliding friction. Well, in my opinion, it's not. I think there's some very clear reasons why shaft resistance due to wedging is distinctly different from shaft resistance due to sliding friction. It's not just a modified version of sliding friction. To begin with, during installation, the radial stresses that act along the tapered portion of a shaft continue to increase behind the toe of a tapered pile as a result of this additional cavity expansion. On the other hand, if you have a constant perimeter pile, a circular, square, whatever, these radial or horizontal stresses remain constant. So the point I'm getting at here, when you drive a pile into the ground, the toe creates a cavity. regardless of what the geometry of the shaft is. What I'm talking about here is what happens behind that initial cavity opening, or cavity creation as we call it. If you have a traditional constant perimeter pile, the radial stresses remain constant. Once you've created this cavity, there is no further expansion of it because the shaft has a constant diameter or constant width. But I've shown you with the animated GIFs that with a tapered pile, after you create this cavity in the ground, you get further cavity expansion due to the taper. Under axial compressive loading, with a tapered pile, you continue to get additional wedging. This is really quite amazing in my mind, because essentially what we're saying here is the more you load a tapered pile in axial compression, the more shaft resistance you get. Why? Because we're opening that cavity further and we're increasing the radial stress around that cavity. Because we're not going to reach a limiting pressure until settlement levels well beyond what we would encounter either in a load test or practice. On the other hand, if we have a shaft at constant perimeter, we know that the shaft resistance due to sliding friction tends to max out, if you will, under relatively small settlements, and will happen in most cases, or many cases at least, will actually decrease with further settlement. And that's because the soil strength along the shaft transitions from the peak to the constant volume or critical state value. So again, during axial compressive loading, with a tapered pile, you continue to get more shaft resistance. However, with a constant perimeter pile, the shaft resistance will actually peak, but actually decrease with further settlement. Now, quite a significant difference. So again, I think there are significant differences that warrant defining shaft resistance due to wedging as a third resistance mechanism for deep foundations. And again, I'll show you an animation so you can see these differences. So what I'm showing you here are just simple animations showing that if I have a constant perimeter shaft, during initial driving, I create a cavity under the toe, I create a horizontal or radial stress, and with further driving, that stress remains constant because the geometry of the pile is constant. However, with a tapered pile, after I create the cavity, I continue to get additional radial stress increase due to further cavity expansion. And that cavity expansion is not occurring with this constant diameter, constant width pile. Same thing under post-installation axial compressive loading. When I load this constant perimeter pile in axial compression, the radial stress remains constant, and the actual frictional resistance will peak and then drop off to a constant volume or critical state value. Whereas with a tapered pile, literally the more we load it in axial compression, the stronger it gets in terms of shaft resistance. Two very different mechanisms, no matter how you slice it. This is not some modified version of this, as it has been treated historically. If we look at some examples, again, from Kennedy Airport, where they have used tapered piles going back to the 1940s, and again, if you could view my YouTube narration on presentation on Kennedy Airport if you're interested in more information. I just assembled some load test results here, and what I've plotted is what I call the compressive resistance efficiency, which is just the maximum applied load. Some of these piles were loaded to what I would consider to be pretty much the geotechnical ultimate limit state, 2-3 inches as pile head settlement, 50, 75 millimeters of settlement. Some were loaded close to failure, but not I include them anyway. So all I've done is max load divided by the pile volume, and I non-dimensionalize it to the unit weight of water so we don't have to worry about units. And I plot that against the pile taper angle. Obviously, a constant diameter pile has zero taper angle. And although there is some scatter in the data, very clearly there is a trend of increasing. The larger the CRE, the more efficient the pile. Essentially, the bigger the CRE, what we're saying, you get more load bearing per unit volume, whether you're talking about cubic foot, cubic yard, cubic meter, whatever, you get more load bearing per volume of the pile. Clearly a trend of increasing with taper angle. And we see, again, when it comes to pile taper, little goes a long way. Look how even for timber piles, very small taper angles, 0.2, 0.25, 0.3 degrees of angle, very, very small taper angles. Look how much more efficient, relatively speaking, they are compared to constant diameter. These happen to be steel pipe piles in this case. Well, let's talk about end bearing. This is another example from Rovinsky's doctoral work. And again, before we talk about end bearing, I want to highlight here the shaft resistance. This shows up more clearly. Again, the dark dots here, these are lead shot that were x-rayed and exposed in the x-ray. And initially, these were all horizontal layers of lead shot. And then Rovinsky pushed these model piles into the sand. So I'm just highlighting here what I've already talked about, that for a constant diameter pile, the shaft resistance is occurring along a zone. Look how far out from the shaft of the pile we have settlement, right? All these beads, all these lead shot were originally horizontal. Look how they curve down. Well, I want to focus really on the toe. And what you see here is that the lead shot forms very nicely a nice soil wedge or triangle beneath the toe. Now keep in mind that nature formed this wedge on its own. All of these lead shot were initially placed horizontally. So as this model pile was inserted in the ground, nature rearranged itself to create the soil wedge. Now the point I want to make here is that the traditional bearing capacity solutions that we use, and there's any number of them that we can find in the literature, they're all based on the assumption that the toe resistance is a function of the vertical stress at the toe level. All right, and if this were a shallow foundation, we would call this foundation level. But they're all based on the assumption that it's the vertical stress, and in a fine coarse-grained soil, this would be vertical effective stress. And you see that they all include some rather fanciful failure mechanisms, none of which we see occurring below this model pile. All we see is this soil wedge forming. Now, Berezantsev and Vesage in the early 60s, they probably came closest to saying that identifying a failure mechanism, but again, they still based their work on the vertical effective stress. Well, the point is that since the 1970s, we've realized that is actually a better model for what happens beneath the toe of a deep foundation is what we call spherical cavity expansion. All right, we previously talked about cylindrical cavity expansion. Now we're talking about spherical cavity expansion. What we're saying is that the failure mechanism beneath the toe of any type of deep foundation is better represented as this wedge. Nature is going to form this wedge whether you put it on your pile or not. That this wedge of soil, which becomes essentially part of the deep foundation, is going to be pushing aside these spherical zones on either side. And one of the interesting things about spherical cavity expansion is that it is based on the horizontal stresses. And you see now why I was emphasizing KO earlier in my discussion of site characterization. K-sub-O is, in my opinion, probably the most significant stress state parameter for deep foundations. It governs what happens along the shaft by virtue of the KH-KO ratio, and now we see that it really governs what's happening at the toe, because spherical cavity expansion is dependent on the horizontal overburden stresses, not the vertical. And this dominance of KO for toe resistance of deep foundations is corroborated by decades of research with the cone penetrometer. There has been all sorts of high-quality research done around the world that has shown that the uncorrected tip resistance beneath the cone penetrometer is controlled by the horizontal, not the vertical overburden stresses. And this is why we've been able to, not we, but researchers, other researchers have been able to develop correlations between cone penetrometer tip resistance and KO, because it's really KO that is dominating the tip resistance of a cone penetrometer. So the conclusion that we draw is that it's KO and horizontal stresses dominate all aspects of deep foundation resistance, both in axial compression as well as axial uplift. They control the shaft, whether that shaft is constant perimeter or tapered, and they control the toe resistance as well. So this is really a major paradigm shift, and why I said early in this segment on axial resistance that the methods we have for all types of deep foundations are based on mechanisms that we dreamt up back in the 1950s. And we've learned a lot in the almost 70 years since then, and we really need to improve the way that we model not just tapered piles, but all types of deep foundations. Another consideration with this myth element of a single value geotechnical ULS relates to residual loads. Residual loads are I mentioned them earlier, they're the proverbial elephant in the room of deep foundations. We've known about them since the 1950s, but routinely to the present, both practitioners as well as academic researchers, with few exceptions, ignore them. We know they're there, but we make believe that they're not there. And unfortunately, we come up with all sorts of elegant theories assuming that they're not there, but they are. What I'd like to show you is two things. First of all, residual loads are there. They're there, I think, for all types of deep foundations. And they influence the outcomes in a variety of ways. And the point I'm trying to make here is that we really need to consider residual loads much more in practice. The bottom line is all stakeholders, and what I mean is licensed professionals in routine practice, academic researchers, really need to rediscover, and I emphasize the rediscover because we've known about residual loads since the 1950s, if not earlier. We need to rediscover residual loads, that they're an inherent consequence of deep foundation installation, and they can't be swept under the rug or ignored, as we've done for decades now. We need to consider them because they penetrate the geotechnical and structural aspects of practice and research. And I'm going to back up this statement by illustrating a number of different elements of deep foundation performance. First of all, you'll often hear people say, well, residual loads only occur with driven piles. Well, Fellinius, and Fellinius, of course, has an outstanding reputation in the deep foundation industry, well deserved. He's presented case histories, and we're not talking about pie in the sky research here. We're talking about case histories on real deep foundations, where he's shown that residual loads develop, yes, they develop with driven piles, but they also develop with drilled shafts, bored piles, as well as jack piles. And I think this probably suggests that they develop with other types of deep foundations, such as micropiles and helical piles that are very much in vogue these days. I think people have not looked at residual loads with micropiles and helical piles. That's why you don't see them talked about. But I think it's something we should do. We should do some research to look at residual loads that develop with micropile installation as well as helical pile installation. So the bottom line is, whether you drive or drill or torque something into the ground, you're probably going to develop some residual load within the shaft of that element as a result of installations. Another claim is, well, they're a geotechnical issue. They disappear when we apply axial loads, so I could ignore them. Two things. First of all, this is very overly simplistic. It tends to be unconservative. And whenever you have something that's unconservative in geotechnical engineering or foundation engineering, it's now in the realm of potentially unsafe. Number two, the reality is that residual loads affect all aspects, both geotechnical and structural, as well as resistance verification, all right, load testing, dynamic testing. So the bottom line is, residual loads are not just some geotechnical problem that kind of disappears. They impact everything we do structurally and geotechnically. And again, I'm going to show you some examples. So let me now go through a variety of applications that will back up these things that I've stated here. Well, let's look at what the basic problem is if you're not familiar with residual loads. Again, what we're saying is that after you install a deep foundation in the ground, and I want to emphasize we're not just talking about tapered piles here. After you install a deep foundation in the ground, even when there is no externally applied load on the head of that deep foundation element, there is axial compressive load within the shaft. It builds from zero to some peak and then decreases, but does not go to zero at the toe. Well, what happens is that along the upper portion of the shaft, you have some drag load, or negative skin friction if you prefer. You then have a transition zone that peaks out at some what we call the neutral plane, where you have some resistance along the shaft, what we call positive skin friction, if you will, and we have some toe resistance as well. So this is the generic look of what we call residual loads. You have some pattern of compressive load throughout the shaft. Usually this neutral plane is somewhere down closer to the toe than the center. I've just shown it here generically. Usually the peak, the neutral plane, is somewhere down here, and you have some toe resistance as well. This simple animation is just to show you how these drag loads develop along the upper portion of a shaft of a deep foundation element, specifically in the case of a driven pile here. What I'm trying to illustrate is that, as we've known for a long time, I mean certainly well before modern soil mechanics existed, that when you drive a pile in the ground, really is kind of a 2 steps forward, 1 step backward process. So you impact the head of a pile with a hammer, it goes into the ground, but then it will rebound somewhat. You can see that more exactly here. This is some recent research where they put high precision instruments on a pile, and this is where you start at. The hammer impacts the pile, it goes into the ground, and then rebounds, oscillates around, stabilizes until the next hammer impact. I've just inverted this plot because it now looks like what's happening during pile driving. So you start here. This is where the hammer impacts the pile. The pile penetrates into the ground and then rebounds. Now in this case, the rebound is quite significant, oscillates around, stabilizes, and then the process begins again with the next hammer impact. Well, the net difference between where you started and where you wind up, this is what we call the final set, or simply the set of the pile. Usually you see a lowercase s used as the symbol for this. So the important thing here is that every time you hit the pile, you're going to get some amount of rebound. And this is what creates the drag load. Again, as I said at the outside, the beginning of the presentation, when I was talking about definitions, I said that drag loads come from two sources. The conventional is from down drag, where the ground settles relative to the more or less static deep foundation. What happens with residual loads is they come about because the ground now is more or less stable or static in position, but it's the deep foundation, in this case the driven pile, that is rebounding upward relative to the more or less static ground. And this is why the drag load develops. So how drag loads develop, it's very different between residual loads from installation versus down drag, but the net result is essentially the same. You have this downward acting, or what a lot of people like to call negative skin friction. So I just want to illustrate how these drag loads develop during driven pile installation. So again, these drag loads develop to produce residual loads because the ground is more or less stable, but as the result of driving, it is the shaft that is rebounding upward relative to the ground. Well, just to show that this is not just a hypothetical situation, this is a pile from the 1969 NGI test program I referenced previously. This was all a coarse grain soil site. Now I purposely chose a constant diameter pile so that we're not bringing taper effects into the discussion here. What I'm showing you here is whether we use K sub H or K sub H non-dimensionalized to K sub O, that I'm showing you three load cases on this particular pile. The dash green curve in each case is the residual load after driving. The red curve that's labeled half Q90. Q90 was the NGI's definition of the geotechnical ultimate limit state or failure load on these piles. Half Q90 would be essentially a working load on the pile. That's the red curve. And the solid green curve would be under Q90 or the geotechnical ultimate limit state. And what I'm showing you highlighting under the service load, here's the neutral plane. So essentially what we're saying is that almost the upper half of this pile is what, 16 meters long, 50 some odd feet long, that almost half of this pile still has drag load on it, even under what would be a service load type of condition. And then down here we have resistance or positive skin friction. This is not a toe resistance. I'm only showing you horizontal stresses here, horizontal stress coefficients here. Well, the point I'm getting at here is, again, one of the claims is that residual loads disappear when we load a pile. And that simply isn't the case. And in fact, in this extreme case, they had to load this pile completely to the geotechnical failure. In this case, the pile settled over 2.5 inches, 65 millimeters. They had to load this pile to a considerable amount of head settlement just to neutralize the residual loads in the pile. Look what's happening here. This first 4 meters, roughly 12, 13 feet of the pile, you have basically no resistance. There's no positive skin friction because all of this 65 millimeters, 2.5 inches of pile head displacement was used up, if you will, simply reversing the drag load, the negative skin friction, into positive skin friction. That's what we're seeing here. You had to have a significant amount of settlement just to reverse the direction of shaft friction acting along this pile. Now, admittedly, this is an extreme case, but nevertheless, it points out that residual loads don't magically disappear as has often been claimed. Well, let's look at the impact on static load tests. Here's a typical static load test that we see all the time in practice. Toe resistance, shaft resistance, total resistance at the head. All three of these curves are wrong. This is from a Fellini's case history. This happens to be, by the way, a jacked pile. Just to show you that residual loads develop with piles other than driven deep foundations. Fellini has labeled these as false because in the traditional static load test, we're basically starting everything at 0, 0. Essentially, in the plotting that we use, we say, okay, I now have, in this case, it was a jack pile. The jack pile's in the ground. There's no shaft resistance. There's no toe resistance. Now I'm going to apply a load at the head. Well, that's wrong. There were significant shaft and toe residual loads already locked into this jacked pile. So what I'm trying to show here, in particular with the toe, is that the toe resistance didn't begin here. The toe resistance in reality is beginning here. Right? Because this is what happened when they jacked the pile in the ground. This was the load settlement path that was followed. So, I mean, in very simple terms, if this were a driven pile, what we're saying is, let's say you had a driven pile and you took 1,000 blows to drive it in the ground. When you perform a conventional static load test on the pile, you think you're beginning from 0 in terms of mobilized shaft and toe resistance on the pile. You're not. As far as that pile is concerned, your load test is only blow number 1001. Your load test is only picking up where that 1,000 blows has left off. The toe resistance is not 0. You're beginning from some point here. The shaft resistance is not 0. So the point I'm trying to make here is that the conventional plot of a static load test does not show what is really happening within that deep foundation element. This is the true behavior, if you will, when you take residual loads into consideration. And this is not a trivial issue, folks, because no matter whether you define, again, as I pointed out earlier, in typical practice, we often use a displacement criterion to define the single-valued geotactical ultimate limit state or failure load. Now, whether you use the Davison offset limit that's popular in the United States, you use a toe criterion that's popular in Europe. What Fellini is showing here is that this would be the quote-unquote failure load for this jack pile using traditional displacement criterion, something in excess of 6,000 kilonewtons. The real, if you will, failure load is somewhere around 5,000 kilonewtons. Quite a bit different. And again, the reason I'm highlighting the failure load is that when we use LRFD for design, LRFD forces us to come up with a quote-unquote failure load to plug into the design formulas. So in conventional LRFD design, this would be the failure load that you would plug into your design equations, something in excess of 6,000 kilonewtons. And in fact, LRFD would say, well, you ran a load test, so therefore we're going to be more generous with the load and resistance factors we allow you to use. You know, we're arguing whether it should be 0.35 versus 0.4 or something like that, let's say. Well, the reality is that the real quote-unquote failure load is almost 20% lower. It's down here, 5,000, not 6,000 plus. So, you know, we're quibbling about small variations in load and resistance factors, where in reality, we're using a failure load that's wrong by about 20%. I think the point's been made. And as you might gather, I'm not a fan of LRFD. I think it's a good concept. Certainly in structural engineering, it may make a lot of sense where failure is very well defined. Structural materials rupture, they break. There's no ambiguity as to what the failure load is or the failure stress or the strength is. Things are a lot different in geotechnical engineering. In geotechnical engineering, we're forced to come up with single value failure loads when in reality there is no single value failure load. And we've got to be, well, I'm trying to say here, I'm not saying we should abandon LRFD, but we got to be very careful when we use it. And this plot here is case in point. Well, if you have an instrumented static load test, you can really get in trouble sometimes. This happens to be for some monotube tapered piles at Kennedy Airport, some work that was done in the 1990s. Now, in this case, this was a classic case where with the monotube pile, this is cold form steel, closed toe, they drove it in the ground. Only then, after driving, did they place the strain gauges within the inside of the pile shaft and concrete the shaft. So the point is that the instrumented load test only measured the strain in the concrete. So this is where the measured load came from, and they completely missed the very significant residual load that was already locked into the steel portion of the pile. I mean, this is why they deduced from the measured load the pile had no toe resistance, where in reality it had a very significant toe resistance. So you could really get in trouble with instrumented static load tests depending on when the instruments were installed. By the way, this is one of the nice things for that 1969 NGI Holman Island test pile program. They use precast concrete piles where the instruments were embedded during the casting. So the instruments were zeroed out prior to driving the pile. And they then extracted the piles at the end of the program and rechecked the zero readings. So they were able to measure the residual loads directly. So there was very high confidence in those residual loads that I've shown you and will show you in some additional slides. Well, dynamic testing is not immune to residual loads. Again, this is another case history from a Fellinius paper. You can get the details from his paper, but the point is that when we use dynamic measurement technology such as CapWAP, where we interpret signals back in the office after the fact to come up with a load distribution within a deep foundation element, these interpretations are not immune to being affected by residual loads. And all that I'm showing you here is this example from Fellinius shows you that the true resistance in this particular deep foundation differed substantially from the resistance inferred from CapWAP because of the failure of the CapWAP to consider the rather significant residual loads. That's what's shown in the blue curve here. And again, you see in most cases the neutral plane is much closer to the toe than the head. So you had a fairly significant toe resistance that was completely missed and accounted for the difference you see here. Well, hopefully I've shown you that residual loads affect just about everything we do geotechnically with a deep foundation. Now I want to show you how they affect the structural interpretations. This is, again, the monotube pile at Kennedy Airport I showed you just a minute ago. This is the interpretations of the loads and stresses within that pile. And again, you see the neutral plane very typically down about 80% of the embedded length of the pile. Well, if you were doing a structural analysis for this pile, this would be the theoretical shared load that we would use in practice that is based on the traditional assumption that after the pile is installed, there's zero load in the shaft, zero load in the concrete core, zero load in the steel shell, zero toe load. Everything begins from zero. Well, it doesn't, folks. Hopefully you see that by now. Fairly significant residual load, including very large tow load. Essentially, the tow load in this case was 100% mobilized, so that the actual shared load was quite a bit different than the assumed shared load. Okay, because by the time that the pile was concreted and now the concrete core had hardened and load was applied, the steel shell already had a very significant stress in it. So we see the end result is that because of the failure to consider the residual loads and the stresses in the steel shell, steel pipe actually, it wasn't a shell, the steel pipe was actually significantly overstressed, up to 100% in places, whereas the concrete core was doing relatively little work. In fact, by the time you got down to the toe of the pile, the concrete core was carrying virtually no load. That's what we're showing here. There's another structural aspect to this to consider, and again, going back to the Holmen Island piles in Norway from about 50 years ago that I showed you a short while ago. This now, we're looking at the axial compressive forces in the pile shaft. Now again, I want to focus on the 1/2 of the failure load, which is roughly the working load on this pile, or service load if we want to think of it in LRFD terms. Normally when we run a load test or we apply a load to a deep foundation, we assume that the load that is, we're talking about now the force, not stresses, we assume that the force applied to the head of the deep foundation element is the largest force applied to that will occur within that deep foundation element. And then we apportion that force with depth. So what I'm trying to show you here is that under this load level where they apply 230 kilonewtons to the head of the pile, because there were still significant down drag and residual loads in this pile, the neutral plane was down here. In reality, the largest axial force in the pile was down here at the neutral plane and was 20% larger than at the head. So the point I'm getting at here is, from a structural design or analysis perspective, it is incorrect, unconservative, and thus potentially unsafe to assume that the load that is applied at the head of the deep foundation in axial compression is the largest axial force that occurs within that deep foundation element. That was true at the end of the load test when they got rid of all the down drag, all the drag load from residual loads, but at this intermediate service load level was not the case. So again, what I'm trying to say here is that there are structural issues you have to be careful about. You need to consider residual loads in the structural analysis and design as well. Well, I've shown you what might be perceived as negatives with respect to residual loads. I'd like to show you now that there are actually benefits to residual loads. There really are positive aspects to residual loads, and I think we really should be focusing on these. The driven pile industry in the United States for many years now has been using a phrase, a driven pile is a tested pile. And I think we could extend that phrase to say a driven pile is a pre-settled pile. And the reason is that the way I like to think about residual loads, residual loads to deep foundations are broadly similar to what pre-stressing is to Portland cement concrete. Both residual loads and pre-stressing preloads and pre-stiffens the system that's involved. so that we get an overall stiffer load settlement response. I mean, that's why we pre-stress concrete. We anticipate where sections of a concrete element are going to be stressed either due to axial forces and or bending moments, and we judiciously kind of anticipate where those stresses are going to be with the pre-stressing. And in a broad sense, that's what residual loads do to deep foundations. The way that residual loads pre-stiffen or pre-settle a deep foundation is that residual loads tend to preload the toe resistance. And as we know, the force displacement response of a toe of a deep foundation is always softer, less stiff than the shaft resistance. I mean, it's been known for decades now that all things being equal, you have to have a lot more relative displacement of the toe of a deep foundation to mobilize resistance as opposed to the shaft. And again, we're talking about a constant perimeter shaft. So essentially what residual loads do is they preload, pre-stress if you will, at least a portion of the toe resistance. And this forces, now when we apply axial compressive loads, this now shifts the loading to the shaft, which is an inherently stiffer response. And the reason I highlight this for a driven pile is that, as it turns out, residual loads are greatest for driven piles compared to other types of deep foundation elements. And again, I go back to the Holman Island pile I showed you previously. We see that now here we can see the toe resistance here. Again, the dashed green curve, this is the residual load after driving. And we see that in this case, we mobilized about half of the ultimate toe resistance simply by driving. So half of the eventual toe resistance was already mobilized at the end of driving. All right, we, if you will, pre-settled this pile. So that now when the load was applied during the load test, we went from here to here to here. This is where the load test ended. Most of the load test was taken up in moving the shaft resistance from here to here, from the dashed green line to the solid green line. And we can see how relatively little of the applied load worked its way down to the toe. All right, so really we're forcing, residual loads force the applied load to be taken up along the shaft, which is an inherently stiffer response mechanism in a constant perimeter pile. Even more so in a tapered pile, as we'll see. And again, going back to the load test I showed you, we see that here, that this is what I mean. Now this again was a jacked pile, but with this pile, we see that the toe resistance really is not starting from zero, it's starting from here. They already had 1,000 kilonewton load locked into the toe resistance, so that during the load test, you got a much stiffer response from the toe because it already had a sizable, in this case, what, about 40% of its ultimate resistance was already locked in due to residual loads. So this is what I mean. There are benefits to residual loads. It pre-settles the toe load to a very. So the bottom line is that the more residual loads that develops at the toe of a deep foundation during installation or the result of installation, the stiffer the overall load settlement response will be in axial compression. So the more toe resistance you get from residual loads, the better. I think that's a fair statement. And the research today is very clear that driven piles develop more residual loads, especially at the toe, than any other type of deep foundation element. And this is why I said earlier, a driven pile is a pre-settled pile. Is simply the act of driving a pile in the ground as opposed to drilling or jacking or torquing. you simply develop a larger percentage of residual loads, and a good portion of that is going to be taken up in toe resistance, which is really beneficial. That's what I'm getting at here. This is not a negative. For the overall stiffness response of the deep foundation element, in compression at least, more is better when it comes to residual load. So if with a driven pile is a pre-settled pile, the interesting thing is that taper makes it even better. And we can see that here. This is Fellinius's interpretation of the same NGI test piles I've shown you previously. And what Fellinius is showing in this plot, he's just showing you this is the red curve is the residual load in the constant diameter pile. The blue curve is the residual load in the tapered pile. And again, the tapered pile that he's showing you here, this was a partially tapered pile, and the taper angle is very modest. It was only about that of a timber pile. But even at that, look how much more residual load you get, and it's all within the tapered portion. Got a lot more residual load in this tapered pile, and that's a good thing. All right, that's a good thing, because what we're saying is that this pile has been pre-settled and it's been pre-stiffened, and this also contributes to taper benefit. And again, going back to the monotube piles at Kennedy Airport I showed you a short while ago, look at the toe resistance. In this case, it was extreme. The residual loads mobilized 100% of the toe resistance of these piles. Again, with the Holman Island pile, it mobilized maybe 40–50% of the toe resistance. Here was 100%. So this meant for these monotube piles at Kennedy Airport, all of the toe load was pre-mobilized, pre-settled, pre-stiffened. So all of the applied load was taken up by the shaft, and you got a very stiff, very beneficial response. And again, if you think about it, when we do design, it's really a displacement and stiffness-based design. I know in LRFD we obsess on ultimate capacity, but serviceability is a very significant consideration in all civil engineering designs. So to conclude the discussion of residual loads, I like this quote from Bucky Fuller: "Don't fight forces, use them." So what I'm trying to say here is, look, residual loads exist. They probably exist in all types of deep foundations. I think we should look for them in helical piles and micro piles that are very popular nowadays. They probably exist with those as well. We know they exist with driven piles, with drilled shafts or board piles, jack piles. Residual loads likely exist with all types of deep foundation elements. We should not ignore them, because ignoring them can be dangerous, both geotechnically and structurally in some cases. But they are beneficial. We should, in fact, to a certain extent, we should welcome residual loads. And quite honestly, nothing develops residual loads better than a tapered pile. And as long as you are properly designed for them, as long as you are properly designed the structural components, the shaft, the core, whatever, for these residual loads, these are quite beneficial. So we need to look at the good and the bad, work with nature and not fight nature. And that's essentially what we're saying here. So to wrap up this segment on axial resistance, some of the conclusions we can draw is we need to really have a zero-based reassessment of geotechnical resistance mechanisms. They date back to the 1950s. The concept of one-dimensional sliding along the shaft of a constant perimeter deep foundation is wrong. The assumption that vertical stresses control toe resistance of a deep foundation is wrong. We need to go back to the drawing board. We need to revisit things, revise things, And we need to explicitly consider residual loads in this process. We've been ignoring them since the 1950s. They exist. There's dangers in ignoring them, and there's benefits to considering them. So we need to look at both the positives and the negatives of residual loads and simply deal with them appropriately. We need to be careful in the structural design of composite deep foundations. If you have, for example, a tapered pile that consists of a steel pipe that is driven in the ground and then concreted afterward, we need to understand that that concrete pipe is likely to have very significant residual loads. We need to be able to estimate what those residual loads are, design the steel component appropriately, recognize that the concrete core is not doing as much work as we think it is in our design. And because of the fact that this single value geotechnical ultimate limit state or failure load is a outright myth, I think we can make a legitimate case that we should pay more attention to load settlement behavior. If we think about it, we recognized early on in the 1950s that with shallow foundations, whether we're talking about footings or mats or rafts, whatever you want to call them, or piled rafts, shallow foundations, with few exceptions, the design and behavior is governed by settlements, right? Not by the bearing capacity. There's no reason we should not be paying greater attention to the load settlement behavior of deep foundations as well. We've been focusing exclusively on the ultimate limit state or failure load of a deep foundation, and LRFD has forced us into this even more. I think we need to take a hard look at considering. And again, this is not just my opinion. Professor Felinius, Dr. Felinius is a well-known expert globally in deep foundations, and he's been saying this for years. We really, really need to look more at deep foundation settlements and not just obsess on the geotechnical ultimate limit state, which in reality, in some cases, doesn't even exist at all, or where it does exist could be a very large range in values. Well, if we realize that we need to take a closer look at load settlement behavior, this now opens up the potential for a new stiffness-based approach to things. And this ties into some of the things I showed you earlier, the recognition that load transfer between the shaft, constant perimeter shaft, and the adjacent ground occurs in a zone around the shaft. And we get a settlement trough just like we find with shallow foundations. And there's actually a theory of elasticity solution. Actually, it's a series of solutions that we refer to as the Randolph-Roth problem. That is not perfect, but it replicates a lot of the observed behavior we see with deep foundation behavior, and has already been adapted for use with deep foundations to some extent. I think we could do more with this and should recognize that deep foundation behavior and axial compression is a settlement problem. It's governed by soil stiffness, not strength. Just to give you an idea of some of the state-of-the-art methodologies that have been developed in recent years that take advantage of this. Here we're looking at a small strain shear modulus profile, and what's different from what I showed you earlier is this plot has just been rotated 90 degrees compared to what I showed you on an earlier slide. The point I'm getting at here is we're just looking at the stiffness of the ground. All right, this is a small strain. Here the researcher used Gmax instead of G0, G0, same thing. This just says this is the profile of the small strain shear modulus, did a straight line fit to the data. This happens to be, by the way, for a board pile or drilled shaft. So we're just looking at ground stiffness, right? No strength. There's no phi angles, no undrained shear strength, anything like that. Just looking at stiffness. Well, if you just run ordinary static load tests and all you need is load settlement data at the head of the pile, you don't need, or the deep foundation in general, you don't need to have instrumentation or anything like that. Just take ordinary load settlement data. You can develop empirical relationships, and there's different relationships for driven piles and bored piles and jack piles and augered piles. We could go on and develop one for micro piles. We could develop one for helical piles. So any type of deep foundation element, might even extend these to ground anchors perhaps if you wanted, vertical or horizontal. And you take the solution to the Randolph-Roth problem, which just relates the load applied to the head of the settlement, settlement of the head of the settlement, and the ground stiffness, shear modulus. Now this equation looks very complex, but it's just algebra, all right? We have about half the Greek alphabet here, but these are just parameters. These various parameter here just relate to the diameter of the deep foundation and the Poisson ratio of the ground, the length of the deep foundation. Nothing exotic here. This is just geometry. Relatively simple, just looks complicated. Well, we'll put all this together, and this is the end result. You get a complete load settlement curve, and in a process that is quite generic, doesn't need any fancy proprietary software. You could do this on a spreadsheet. Of course, being a former professor, I would probably make my students do it by hand once just to see how the process goes. But realistically, in practice or research, we would do this on a spreadsheet. And you get a complete load settlement curve. So fine, if you are using LRFD and you feel that you need a single valued ULS value or failure value, you could go into your generated load settlement curve and pick off whatever failure load you need for your LRFD analysis. But something like this gives us much more insight into the behavior of the system. And notice, of course, that this process inherently takes residual loads into account. This process does not inherently consider, or explicitly, I should say, does not explicitly consider residual loads, but to the fact that the residual loads are baked in, if you will, to the load settlement behavior in the load test, it is reflected in this final result. So this is not perfect. I have some issues with the process I discussed in some of my publications, but at least it's a step in the right direction of forcing us to look at the complete load settlement behavior instead of obsessing on some singular failure value. Okay, I now want to talk about resistance forecasting methodologies. Now that we've talked about how we should calculate and forecast the resistance of tapered piles, now we'll talk about how it has been done to date in practice. And by the way, I like to use the term forecasting in lieu of prediction. I know that the term prediction is well established in civil and geotechnical and foundation engineering. I just think forecasting is a better term for prediction. It's useful to always remember where we started. It wasn't all that long ago, the middle of the 20th century, when even Terzaghi himself was saying that when it came to deep foundations, and at that time really driven piles were the only game in town, pretty much the only game in town, that he was saying, look, there's no way to calculate the resistance of a deep foundation. You either have to go on local experience as to what works, what doesn't work, or perform a static load test in the field. Basically, there was no calculation methodology available. And of course, this was an era when we were still installing piles using a steam-driven impact hammer. So it's useful to remember where we started from. We certainly have come a long way, but I think we have a ways to go to make things even better. Analytical methods for forecasting resistance of deep foundations to axial loading have historically focused on compressive loading. The vast majority of methods that you see that have been developed since the 1950s only talk about compressive loading explicitly. Uplift loading has typically been treated as an afterthought, where you just simply reverse the compressive loading, subtract their toe resistance. So typically for uplift loading, you say, well, whatever you calculated for the shaft, use that for uplift. You don't have any toe resistance. That might be okay for constant perimeter deep foundations, but it really does not work at all for tapered piles. As I indicated earlier, this approach to uplift loading has allowed the development of proliferation of a lot of misinformation about the uplift resistance of tapered piles. Having spent a good portion of my professional career in engineering practice, I've run into many people over the years, both civil engineers and architects, who said, well, you know, I thought about tapered piles, but in this case, we have significant uplift loads. Tapered piles don't have any uplift resistance. They just lift out of the ground. And that simplistic view of things is simply incorrect, as I showed you previously with the unwedging mechanism. There are two broad approaches that have been used to date for crafting resistance forecasting methodologies, dynamic and static. And the dynamic preceded the static by about 100 years. So we'll talk about the dynamic approach first. Really dates back to around 1850, and this was an era when drop hammers were being used for most, if not all, pile driving. Initially, pile driving was treated as a simple problem in physics, and there were two different approaches that were used. The first one was actually based on work equivalence, work in this case being expressed as some force going through some distance. You have the weight of a pile hammer, it drops a certain distance, that produces work. And the more sophisticated was based on rigid body impact, but both of them, the unifying concept was that the pile was assumed to be a rigid body. And then when impacted during driving, the entire pile displaced downward a uniform distance or set with each hammer blow. And no matter how you approach it from either a work or rigid body impact perspective, you actually wind up in the same place. You wind up with a formula, and Chellis, in his well-known 1961 book, talks about 24 different formulas, what we call pile driving formulas nowadays, the most well-known of which is the so-called Wellington or engineering news formula. Most people know it as the engineering news formula. It's actually originally known as the Wellington formula. Wellington happened to publish it in Engineering News, which is how the Engineering News name came about. A completely different concept based on one-dimensional wave transmission through an elastic rod was developed by Isaacs around 1930. And this was revolutionary in that it assumed that the pile is always flexible during driving. And let's once and for all realize that E.A.L. Smith did not, quote unquote, invent the one-dimensional wave equation in 1960. Having taught undergraduate geotechnical engineering for almost 30 years, I can tell you that every English language textbook I've ever seen refers to Smith's 1960 paper in ASC Geotechnical, well, Soil Mechanics Division, then journal, as being the quote-unquote invention of the wave equation. Number one, Isaacs thought up this concept 30 years earlier. Number two, Smith was actually a mechanical engineer, and he actually published his work related to the wave equation earlier in the 1950s in mechanical engineering publications. But for some strange reason, Isaacs is not given the credit he deserves for really coming up with the wave equation, or what we refer to now colloquially as the wave equation. But regardless, whether you use a rigid body or rigid pile or flexible pile approach to things, no dynamic methodology considers the wedging mechanism of tapered piles or even takes into account the unique geometry and geotechnical resistance of tapered piles. The best that some of these equations do, like the wave equation, is they allow for the fact that the pile cross-section gets smaller with depth with the tapered pile. But the bottom line still remains that any dynamic methodology, that includes things such as pile driving analyzer and CapWAP and some of the post-installation or installation monitoring methodologies we use, they are inherently correct when applied to tapered piles. They just don't take the wedging into it. As far as the static approach really dates back to what I call modern computational foundation engineering, which began in the 1950s, and is based on the traditional resistance mechanisms of shaft resistance due to sliding friction and toe resistance due to end bearing we've talked about. And most importantly, it ignores the existence of residual loads from installation. So right away, we see that traditional static resistance forecasting methodologies have a built-in or baked-in error in that they ignore residual loads, which is a real problem. Hopefully you understand that now. However, people did recognize the taper benefit beginning in the 1950s. There are a number of different approaches have been used to model and quantify taper benefit since the 1950s, but they always treat it simplistically either as an enhancement or increase to the traditional shaft resistance due to sliding friction. They do not consider it to be a standalone third resistance mechanism as it really is. They just say, well, tapered piles have more frictional resistance. Or they use some sort of empirical gimmick to model the taper as some combination of sliding friction and end bearing using what I call the donut on a stick model. The important thing is that no static approach methodology developed to date for use with tapered piles correctly considers the two-stage taper benefit based on cavity mechanics that replicates actual tapered pile behavior. And again, hopefully you appreciate now that installation is a very, very big part of whether or not taper benefit will develop. A taper-driven pile will develop a lot more taper benefit than a taper drilled shaft, for example. So how that tapered deep foundation gets in the ground is really much more important than what happens during axial compressive loading. None of these methodologies consider residual loads, which, as I've showed you, are more significant for tapered piles than any other type of deep foundation element. There's conclusive research that residual loads develop to a much greater and much more significant extent for tapered piles than any other type of deep foundation, including constant perimeter driven piles. And certainly no static approach correctly models the uplift resistance that is behaviorally unique to tapered piles. It doesn't consider the complex unwedging that occurs. We can categorize static resistance forecasting methods two ways. We have what we call indirect methods. Some older publications, you'll hear them referred to as rational methods, and these are based on geomechanics principles. And then there are direct methods that are purely empirical and based on some load test database, right? You measure something in a cone penetrometer sounding, you plug it into some empirical formula and says the shaft resistance is this, the toe resistance is that. Both of these began to evolve at the same time in the 1950s. Initially, indirect methods were more popular, but with the much greater use of cone penetrometers in recent decades, direct methods have become a lot more popular. We can categorize these static methods with respect to tapered piles in a couple of different ways. To begin with, there are methods that were developed specifically with tapered piles in mind versus methods that are essentially versions that were developed for constant perimeter piles. For example, the Bjerrum-Berlin-Fellenius beta method. The beta method is very, very popular in practice. This was developed solely for a constant perimeter pile database, but it's been repurposed and modified using the so-called donut on a stick model. And what I mean by that is you take a segment of the actual tapered pile and you artificially decompose it into a constant diameter portion and what I call a donut portion. So this allows you to say, well, I have a method that was developed for constant perimeter piles. I'll calculate a pseudo shaft resistance for the stick and a pseudo end bearing for the donut and add them together, and that will give me the behavior of the tapered pile. Unfortunately, I've yet to find any published work that supports use of a gimmick like the donut on a stick model. No shortage of people going around saying you should use the donut on a stick model, but it would be nice to see that it actually gives you correct results. In some of my publications, I have done some comparisons using this donut on a stick model, and I've not found it to be even remotely accurate for tapered piles. So if you want to use it with caution. That's my only suggestion. So I'm only, however, going to talk about taper-specific methods. Most of the methods developed specifically for tapered piles have been indirect methods, and again, they assume the traditional mechanisms of shaft sliding friction and toe end bearing, and taper benefit is just treated as an enhancement or increase of shaft friction, not as a true third independent resistance mechanism as it really is. So these indirect methods fall into two categories. One is based on a two-dimensional equivalent or pseudo retaining wall model for wedging. And in this, the stage 1 and stage 2 wedging are lumped together. Right, this has only been developed for driven piles, so it kind of lumps the stage 1 and stage 2 behavior together. There is a three-dimensional cavity expansion model for wedging, but very unfortunately, it only considers part of stage 2 only, and that's a real shortcoming. The researchers who develop it and others who have used it clearly don't appreciate that the stage 1 wedging is really the more important part. And that's unfortunate because it does use cylindrical cavity expansion, so it's on the right track, but it does not properly apply it. And as a result, there's some really, I think, incorrect conclusions drawn about taper benefit. The 2D wedging model based on pseudo retaining wall model is applicable for coarse grain saws only. And of course, this work was done by Nordland. And what a lot of people don't realize, if you open up again, having taught geotechnical engineering for 33 years, if you pick up any English language textbook, you look at the Nordland method, and they only reference Nordland's 1963 paper in an ASCE journal. But in reality, Nordland revised this method in 1979. So there's two versions of the Nordland method, and actually they can yield some very, very different results. There are some significant changes in the revised version in 1979 that really reallocate the toe and shaft resistances considerably. So you have to be very careful when you use the Nordland method. Almost 20 years ago, I developed a modified version of the Nordland method that I've used in a number of my publications the last 2 decades. The 3D wedging model based on cylindrical cavity expansion really has its origins with Kodakara and Moore, 1993 ASCE journal paper. Their method was developed for all soil types. Again, unfortunately, they did not appreciate that the stage 1 wedging. And in fact, for their only case history comparison, they used a rather obscure paper from the former Soviet Union, Russia, present-day Russia, that talks about a tapered drilled shaft or board pile. How one can drill a tapered hole in the ground and keep it stable before it's concreted, I have no idea, but unfortunately, that was a very poor case history to use because there is no stage 1 wedging benefit with a drilled shaft, obviously. So they drew some very atypical conclusions about tapered benefit from this. And I say it's very unfortunate because Manandhar, in his doctoral work, along with several colleagues in Japan, made a number of very modest tweaks and modifications to the Kodakara-Moore method over a period of years for coarse grain soils only. And unfortunately, though, since they based their work on the Kodakara-Moore model, they extended these very incorrect interpretations. They did not take the stage 1 wedging into account. And that's where some of these conclusions come about that, gee, it's better to put the tapered section above the constant diameter section of a partially tapered or semi-tapered pile that I cautioned you about earlier on in my presentation. And finally, there's work done in Canada by El Nagar and Sacker and some of El Nagar's doctoral students. It's a much simplified version of the Kodakara-Moore method, applicable only to coarse grain soils. Again, unfortunately, just propagates the inherent errors in the Kodakara-Moore method, which only include a part of stage 2 wedging only. Quite unfortunate. Now, direct methods fall into 2 broad categories, and they've only been applicable to coarse grain soils. We have empirical methods, as well as a method based on a cone penetrometer sounding and use of the donut on a stick model. The empirical model has been used by Meyerhoff, had 2 versions of his method. In one, he said increase the shaft resistance for taper, and the other, actually initially he said increase the toe resistance, then about 20 years later he said increase the shaft resistance instead. But these were just empirical, multiply it by 1.5 type of thing, one size fits all. The only direct method explicitly developed for tapered piles is the Togliani method, based on cone penetrometer data. But again, unfortunately, Togliani uses the donut on a stick model, and I find the results from the Togliani method really are quite inaccurate. Okay, I've talked about how tapered piles actually develop axial resistance, and I've talked about what existing resistance forecasting methodologies can and cannot do. Clearly, there's quite a gap between these two, which leads us to now talk about what our priorities should be for research and development with respect to tapered piles. Let's look first at the geotechnical aspects. At the top of the list is a need for a comprehensive indirect method for forecasting the axial load resistance of tapered piles. And I feel that it's best to concentrate initially on an indirect method as opposed to a direct method, because with indirect methods you explicitly see all the different contributions. You see the forces, the stresses, the displacements. It's very clear what is happening from a geotechnical and structural perspective. Direct methods are very easy to use, which is their primary attraction, but they are only as good as the database used to create that method. Because with a direct method, you say you measure values in a cone penetrometer sounding, you put them into some empirical formula, and here's your shaft and toe resistance. It's very attractive to use, certainly in routine practice, but you're at the mercy, as I said, of what is in the database that went into that method. And certainly a direct method might be something to develop for tapered piles somewhere down the road, but not in the immediate future. First and foremost, the method has to properly model stage 1 wedging that develops at the result of the initial pile installation. And this is terribly critical because this is where most of the taper benefit comes from for tapered piles. It is where the taper benefit, or much of the taper benefit, is lacking for, say, a drilled taper element or a tapered element installed in some other manner, say by vibratory hammer. And this is where methods such as the Kodak-Harrer-Moore method and all the derivative work by Menand-Har et al. And El Nagar et al. Fall short, completely overlooks the stage 1 wedging. And unfortunately, some, I think, problematic conclusions have been drawn from that incorrect work. So really, this is quite essential. The method has to include an explicit consideration of residual loads. And one of the interesting things is whether or not these residual loads vary with time after driving. We know residual loads exist, and we know they are relatively largest for tapered piles compared to any other type of deep foundation element. What we don't know, at least I have not seen any published work along these lines, is whether these residual loads vary over time. If they vary over time, it is likely because of a change in ground stiffness. One of the things that Felinius and his colleagues found from the 1990s instrumented pile load tests on monotube piles at Kennedy Airport was that all of the increase in pile resistance was due to soil stiffness, not strength. Again, we've known for several decades now that piles, especially tapered piles driven into coarse grained soils, will appear to gain resistance over time. If you drove a tapered pile in sand, the load settlement curve you would get a day, a week, a month later, they will all vary. And the pile will appear to, quote unquote, become stronger, gain more resistance with time. And what Felinius and his colleagues found was that this gain in resistance was due solely to ground stiffness, not to strength. This wasn't like driving a pile in clay and you have consolidation and the soil gains strength. I mean, we've known that for many, many decades now. And this is why I keep coming back to the importance of stiffness in modern deep foundation engineering. There are things that go on with deep foundations that appear to be related to ground stiffness and not soil strength. So we need some fundamental research into not only residual loads, but do residual loads vary with time, and how that any change might be related to a temporal change in ground stiffness, specifically the small strain shear modulus. Because it's quite possible that any variation in residual loads may be producing this apparent gain in resistance that we see We need to explicitly and separately model the stage 2 wedging that comes from external post-installation loading and axial compression. And we should get a complete forecast of load settlement behavior as an outcome of this. Again, we should be moving away from just focusing exclusively on some geotechnical ULS or quote-unquote failure load and looking at the complete load settlement behavior. This improved model should include unwedging, cylindrical cavity contraction caused by uplift loading, and also produce a load displacement curve for uplift loading on tapered piles. So again, overall, we need to come up with a method that considers each one of these aspects explicitly. As I said, Nordland's work lumps the stage 1 and stage 2 wedging together. Kodakara and Moore's work and other derivative work from that considers part of stage 2 only. Nothing explicitly considers, none of them consider the uplift loading. None of them explicitly considers residual loads. And while the initial focus should be on coarse grain soils, we should at some point in the future extend the methodology to fine grain soils, so that once and for all we can see if there is a taper benefit to fine grain soils. Historically, the assumption has been that there is no tapered benefit for a pile that is founded completely or primarily in fine grain soils. There's been some recent research that has suggested otherwise, but as I said, there is no consensus on this at the present time, so this should be resolved one way or the other. All of this work, we need to consider the effect of pile cross-sectional geometry. I mentioned this briefly early on, but I'd like to elaborate on this a bit more at this point. Clearly, everything I've talked about with cylindrical cavity expansion, things like that, that really applies only to a circular pile. And indeed, certainly here in the United States, the vast majority of tapered piles have, in fact, had a circular cross-section. But there are square tapered piles, and these are precast concrete piles. They apparently have seen some limited use here in the United States. They may have seen some greater use outside the United States. In Nordland's second 1979 publication that is not widely known, he did talk about the geometry issue, and he claims that he did look at square taper piles and found that they had much less taper benefit than a circular taper pile. So again, to the best of my knowledge, there has been no explicit study to date of pile cross-sectional geometry when it comes to taper piles. There is some anecdotal information from one of Nordland's publications that it does make a big difference, and that square taper piles do not have the same taper benefit as a circular taper pile. It is obvious, it should be intuitively obvious, that you cannot have cylindrical cavity expansion with a square. So clearly, with a square taper pile, there has to be some other physical mechanism going on. There is some sort of expansion, obviously, of the ground when you drive a square taper pile in the ground, but clearly it is not a cylinder. Exactly what the shape of the failure surface looks like and what sort of model best approximates that, it's not clear at this point in time. So this is certainly something that has to be considered. In terms of structural issues, we need to do a better job of analyzing the composite or multi-component pile cross-sections, and these are very common with tapered piles. Certainly the predominant tapered pile driven in the United States at the present time, the taper tube, consists of a steel pipe made out of hot rolled steel that is driven into the ground. and then is concreted after installation. Well, clearly that steel pipe has some significant residual loads in the steel pipe long before the concrete is poured inside of it and solidifies. So we need to do a better job to take this into account. So we need to consider residual loads. We need to consider the incremental construction where appropriate. And we should be doing a three-dimensional, not a one-dimensional stress displacement response to the pile shaft, where we consider not just axial loads, but also the radial stress and radial displacements interaction between the pile components as well as the surrounding ground. So we certainly need to do a much better job of how we analyze and design the structural aspects of tapered piles. We need to do a better job with dynamic analyses. Again, analytical methods such as the one-dimensional wave equation that we use primarily in the office for design, as well as related geotechnologies we use in the field, such as dynamic measurements, the pile driving analyzer, the CapWAP analyses. These are all based on a theory of one-dimensional wave transmission in an elastic rod, and this clearly does not apply to a tapered pile. And that's because the wedging resistance mechanism of tapered piles is not correctly approximated by one-dimensional wave mechanics. One-dimensional wave mechanics assumes that the pile particle displacement is entirely longitudinal, one-dimensional, which is not correct for a tapered pile. Wave mechanics only considers the traditional shaft sliding friction and toe end bearing resistance, which is not correct. And we could see the difference by looking at a simple animation. Again, this is a constant perimeter pile. Clearly that undergoes one-dimensional behavior. Whether this is initial driving or restrike behavior, yes, all of the displacement of the pile is in one dimension, the longitudinal direction. All of the resistance is occurring along the shaft due to some frictional mechanism and some toe end bearing. Clearly with a tapered pile, the relative displacement is two-dimensional. We have an axial component and we have a radial component. It is not one-dimensional. And the resistance is coming from three mechanisms. If we have a constant perimeter portion, we have shaft sliding friction. Here we have wedging and we have end bearing. And again, this is very important because going back to what I just mentioned in the previous slide about the recognition that if we drive a tapered pile in coarse grain soils, it appears that the pile gains resistance with time. It's important to understand that all of this implied resistance gain comes from restrike measurements. It does not come from static load tests. It's not like somebody said, okay, I drove a tapered pile in sand, I did a load test the next day, then I did a load test a week later, then I did another load test a month later. No, all of this interpretation we have for the gain in resistance, axial compressive resistance in tapered piles in sands, all of it comes from restrike measurements. Well, think back to what I talked about earlier when I showed you that Fellini has demonstrated that the distribution we get of resistance from a CapWAP analysis tends to be incorrect for tapered piles compared to the true resistance. So the point I'm getting at is, are we really seeing an increase in resistance in tapered piles in sand? Or are we seeing, because again, this is all based on deduction from restrike measurements, which are inherently incorrect for a tapered pile. I've now talked about that in several different ways in this presentation. Or are we seeing some complex behavior where the ground stiffness is changing with time after driving, the residual loads are shifting around, and therefore it appears we're getting a change in resistance, where in reality we're just seeing a temporal change in residual load distribution and perhaps change in ground stiffness distribution. Bottom line, we really need some very, very fundamental research to look into this to get a better idea of what is really going on. And as part of this research, if we're going to base conclusions based on restrike driving of piles, then we need to come up with some sort of three-dimensional wave equation model that is a better model than what we have at present. Well, with that, I have completed all the topics I wanted to cover in this presentation. So it's time to wrap things up. I do include references to some of the specifications I've made throughout this presentation. You could look them up at your convenience if you're interested. And with that, I would like to say thank you. And I'd like to point out that just within the last month or so, I've published a 636-page monograph on tapered piles. And believe me, when I started writing this monograph several years ago, I never in my wildest dreams thought that I could write 636 pages about tapered piles. But there is a lot to say about tapered piles. So as much as I have talked about them over the last 3 hours, and for those of you who made it to the end of the presentation, thank you for your perseverance and interest and attention. As much as I've said in the last 3 hours, there is substantially more that can be said on this topic. So if you're interested, this monograph is available using print-on-demand technology worldwide from any online bookseller. All you need is this ISBN number to look it up. And again, I close out this presentation and say thank you very much for your interest, your attention. I hope you found things of some value. And if nothing else, sparked your interest and curiosity in tapered piles. I think they're a very fascinating type of deep foundation element. They incorporate some unique things that you do not find in any other type of deep foundation. And as a result, they allow foundation engineers to do things you cannot do with any other type of deep foundation. So thank you and goodbye.